can you see this?
Yeah, I can see this. Can you show from which graph did you extract this?
Okay. That was extracted from this graph.
Okay, from this. Okay, now if you plot the histogram of that mathematical data, then do you get a similar result?
Uh, Plot the histogram. Oh, okay.
That would be approximated by this.
Let's see. This. Sorry, sorry about this.
I
Trying to
we cannot
find.
see this. Cannot see the.
Okay, can you see this now? The
Yeah, I
mathematical.
can see.
Okay.
Yeah.
So you want me to plot a histogram?
The
Um,
histogram of the extracted data for background and for.
I mean, so the histogram. So just the um, just the values, right?
Yeah, just do a histogram plot for that table.
It's a binned plot, I guess.
Yeah. Just search in the mathematical help histogram of that table.
So I didn't understand. This is so I've for each bin I have a certain thing. So like to plot a histogram, I need a I need more than one data value at each bin, right? So this is the number of data points at each bin. How would I plot that in a histogram?
Um, you need to the x-axis you needed to approximate. For example, that thing that you were saying that is 100.994.
Yeah,
That is approximately 101, right?
yeah,
That's 103. So it will go like that, and you have a bin of width 3, right?
two.
So you have a bin of width 2 actually. So 101, 103, 105, 107. That's how you are going.
Yeah.
So you have a bin width of 2. Now you should be able to plot, right? Just go to the mathematical help and figure out how to use histograms.
Okay.
Uh,
For each of this, I actually need data which it will then compile into a histogram.
this I the third option is plots histogram with bin heights computed according to the H spec. So actually, you can just plot the second column, right, of this. thing and start from 101. So you just treat the second column as the data x1, x2, right? Those are your data, right?
Uh,
The second column of the table is 3632.
yeah.
Yeah, so you
Yeah. Do you have any idea what the command would be?
what?
Do you know what the command would be for that?
That is that table, and then
H2
the,
would be
yeah, that means all, then 2, comma 2. I think that should be it. Yeah.
uh, but again, this would not give me like
Just print out what this H to GGDP all 2 is.
okay.
See if it is a one-dimensional column.
So this will actually bin these data points into some sort of a histogram. The frequency would come on the y-axis.
This is strange.
Uh, this is already the frequency, right?
But that is your y-axis height, right? The second column is your y-axis height.
Yeah, so that is the number of events, right? Like if I go back here, that's the number of events on the y-axis.
Yeah. So that is the average number of events for 2G bin.
Yes.
Okay. Does anyone else know how to do this in any other code? Suppose given this two-dimensional data, how to plot a histogram?
In Python, I guess the command is hist and first bracket x comma y, and we define the x and y at the beginning of the histogram.
Yeah, it should be doable here as well. So if Anugrah exports you the data, can you plot the histogram in Python?
Yeah.
So Anugrah, can you export this data and send it to Vicky maybe?
Yes. I
Or
will
I can
send.
just tell him if you can share, because I am joining with phone. So you can just use the Jupyter notebook
No,
and
I don't think he has Python. That's the problem.
Yeah.
just go to Jupyter notebook if you have Chrome or any browser. So
Okay.
in Jupyter notebook, you can use just a Python compiler there online.
Okay, let me check.
And from here.
To go to the
Okay.
Python
Yeah, I haven't
and
shared.
Python.
Okay, just a second. Share this as well.
Yeah. From Jupyter, try it in your browser, and then the first one, the Jupyter Lab. Go down,
Right
try
on
it
your. Oh, okay.
browser. There will find first one.
Please try again soon.
I guess so. This is a and if there is too many users, so they take a
Yeah.
time to just refresh it. Or you can just use the second, the Jupyter notebook. Go back. Second, yes. Yeah.
Yeah.
Yes, yes. Just import numpy
Okay.
as np, I guess.
Yeah.
Import
And
math.
it's what?
Import math
Math.
as
Yeah.
just it. Yeah.
As M. Okay. Okay.
Yeah, yeah. As in add a
Oh.
new, yeah, add a new line, go to the plus sign, and there you need to put x and y, the values.
I see. So is it? So should I shift enter or something?
Yes, yes, yes. Enter.
I,
What is the import numpy as np?
yeah. Some error. It's
Numpy resolution at that. Import numpy.
is I supposed to be capital?
Yeah, yeah. Import should be in small. Yeah.
Yeah. Okay.
Then add the x and y, and then it.
So you want me to add the action. So
Copy
how
the
will I?
copy the value x equals to third bracket and the values.
X is equal to this one, and
Just copy the values here.
yeah, so that's 100 to
So
159. I think it's better I just enter
two
the
values at the letter.
genetics.
You have to do it manually. You cannot upload it from some data file.
Yeah, but that is very complicated. I check.
I mean, I have to round
Okay,
this
just
off.
take any. Okay, just first, just take any x and y values there. Just 5 or 6.
Okay,
Because I haven't.
Yeah, you don't have to do the full thing.
full
Just
thing. Yeah,
Yeah, yeah, just check if
first.
it works. Then you can use the whole thing. Because
yeah, yeah.
this few things.
So let's just go up till 111. So that's X, and then I need to give the Y values. That would be 3632 3396
Commands
3342
control enter.
3115 Okay. Control enter. Shift enter.
Sorry, shift enter.
Okay. And then
plt dot hist first bracket x comma y small hist
yeah, X comma Y.
I
hist
think
hist
What?
you are missing a T.
Oh,
plt dot hixt st. Can you make it?
should I be importing some
Yes,
plot
yes, yes.
and PLT as well, right?
Okay, at the yeah, at the beginning import matplotlib as plt. Matplotlib as plt.
There's no attribute hist.
Okay, yeah, you can just share the data. So I will check it later if
It's okay.
I'm missing
Okay,
something.
Okay, I'll
go
show
ahead,
you the
Anugrah, with the
remaining. Yeah.
other things, and we will fix the histogram later. And this is from the fitted background, right?
Yeah. So this is actually the data points. So the data points, these black
Yeah.
dots.
Yeah.
So those are these ones. However, this one I also took because I was not getting a good graph. So the second data set is I've gone over the solid line and picked out the values of the solid line um, at each bin. So corresponding to the bin at say 101, I've taken the data point as well as the value of the solid line. Okay. So the dotted line is the background, but
Yeah.
this solid red line is the fit with the data points, I guess. Um,
Yeah.
so to get a better p-value graph, I took this one also.
You do
Then
not need a better p-value graph. You will get what you get. Yeah. Don't
yeah,
don't worry about that.
yeah, and then I also took the data from this dotted graph, which is the theoretically expected one without the h2 gamma gamma. I mean the z,
So,
the yeah h contribution, yeah,
your actual data are the black points, okay,
black
and
points,
your
yeah.
background is the dotted line, which coincides with the solid line.
Because for the Poisson distribution, um, um, I need since it's discrete, I needed to round it off first, and then this is the
Yeah,
uh,
I mean, for these big numbers, you can just use Gaussian, but okay, if you have used Poisson, it's fine.
yeah. So then the background also I sampled. So after that,
So background you sampled using what? Using
the dotted line.
the dotted line, but away from that.
I've used the solid line everywhere else except here. I've used the dotted line.
Okay, yeah.
And
And then the black points are your data. So if you have used the background estimation the way you said, and then you have used your data, the black points as your data.
then I get
Then
such a graph. Just a second.
I mean, this deep would be even lower, near 125 GB. The p-value should be lower.
So I got something like this. However, if I do use the data points from the fitted line instead of the actual black dots, I would get something like this. Um, but if I use the
That is not the point.
yeah,
You're missing the.
agreed, yeah.
That is not the point. But your p-value at 125 GB, you only get 0.1.
Let me see. It's 0. I think 0.016. Oh no, 0.00124.
That is the thing that I am see, because those are just fluctuations.
Um,
Okay, so this 0.8 to 0.2 will be just fluctuations. So plot it in that scale, and you will see that there are no fluctuations. You have to see the scale in the y-axis. The y-axis should be in the log scale. So in the log scale, these fluctuation will be going away.
oh,
P-value is 0.2 or 0.1 is nothing.
okay. So, do you know how I should plot it in the log scale?
You have done what? This you have done least plot,
Yeah.
and you have joined it.
Yeah, joined is yeah, to join the.
But even this does not look right. So where is your 0.1, 0.001? So it is not showing here, right?
I mean, I guess it's this point over here. Um,
Yeah, it does not tell you the whole story. So I
okay.
think it's either list log plot or log list plot. Check which one gives you the y-axis.
Let's log plot.
So go below. Let's see what it does. It is the y-axis in the. I hope it's the y-axis in the. And you change the thing manually. Change the plot range manually.
Okay, so I'll just change this into list log plot instead.
It makes better sense now.
Yeah, sorry. But I just want to smooth it out a bit more.
Yeah, because you see the plot there in the p-value plot in that paper, and it was in the log scale, right? Because whenever you plot p-value, you are always plotting in the log scale, unless the p-value drops at around 10 to the power minus 3. You do not see anything sensible. Okay. If it is below 10 to the power minus 3,
Hmm.
or actually it's above 10 to the power minus 3, then your statistics is not significant to claim any deviation. Okay. Now you saw the actual p-value plot that this paper had done.
Okay, so that was.
Yeah, here. This is the combined data. Do they have the individual data? The individual 7 and 8 TV? The blue or red lines, right?
Yeah, but I don't know which one is which. I think okay. The blue one is the 2011 one.
Okay. So it more or less so in the minimum value is around 10 to the power minus 3, right?
Yeah, somewhere.
Here, and your value is what, 10 to the minus 3 there as well.
Yeah. So,
Yes, barely touching 10 to the power minus 3. Okay. So yes, this is trustworthy and okay. And anything else? What else did you do?
yeah, that's all.
Okay. So can you go back to those plots? The H to gamma gamma. Uh, this data where they have shown the data.
Okay.
This here, let's say. So from the plot above, okay, like this kind of exponentially falling plot. Here you get in the panel below, you actually obtain a kind of a flat plot, right?
Yeah.
So have you wondered how did you get that? How they had obtained that plot?
Well, they say it's events minus background.
Yeah.
Mm, but yeah, how they obtained it, I don't know.
So that was the our first thing. That is a sampling of data. So first, they have a very good idea of the background. Okay. So they have to separate out background from signal. Okay. So that's why they fit the background with the dotted line. So away from that peak, they fit that data with the background, and then they just subtract it. Okay. They subtract it from the observed data. So they basically each and every point tells you the data, the black dot minus the dotted fit.
Hmm.
Okay, and you see that those are there. Do you see the pattern there?
Yeah, yeah.
Okay, so so that is so this is so remember I told you that to separate out two types of data, you have to construct a test statistic. Okay, and in this case, the test statistic is that fitted polynomial fit actually. Okay. They could have done a better fit, but I think they were happy with this one. And so that is how they can see now the distinctly the peak is there at 125 GeV. So if they remove everything from the background, okay, and that is the pure signal. And that pure signal means, so that is that gives you the pure signal events when you actually when you actually observe, you always observe signal plus background, right? But the in theory you can actually predict how high will be the signal event. For example, we are observing the Higgs boson, and if the Higgs boson has a mass of nearly 125 GeV, okay, here they have used Higgs mass equals 126.5 GeV. So with if I give that as an input to the standard model of particle physics, then every model parameter is known in my theory, and now I can actually simulate. So if I do a proton-proton collision at 70 eV with an integrated luminosity of that femto1 inverse, how many photon-photon events should I observe? Okay, so this H2 gamma gamma, how many photon-photon events should I observe? And that would be this red line in the bottom panel. Okay, so the resonance will be seen near the Higgs mass, actually where the Higgs mass is, and everywhere else it will not contribute. Is it understood? So you can match it with your theoretical prediction. Did it make sense to all? I'm not sure. Okay. So, all right then, Anugrah, you can stop sharing now. I will discuss stuff. Okay. Can everyone see this screen?
Yes, sir.
Good. So today we are going to talk about uh, the third and probably the most important statistical procedure that involves parameter estimation. Okay. Now, let me first formulate the problem. Okay. So the statement of the problem is: suppose you have uh, a random variable x, and uh, which whose PDF are given by fx. So fx comma theta. This is the given PDF for x, and it depends on parameter. Usually this is a continuous parameter, theta. Okay. So basically how the x is distributed depends on the value of theta. So if you change the value of theta, you will get a different distribution of x. Try to keep that in mind. Now suppose you do a measurement on this x, okay, and you obtain so you do n number of independent measurement of this x, okay. So n independent measurements of x, and that you denote by this vector x equals x1 x2 up to xn. Okay, so this is the these are the measurements. So always you will make finite measurements, and now you ask, given this measurement, given this one measurement, what is your best guess for theta? Okay, so given these uh, these values, or given these measurements, uh, what is your best guess for theta? Okay, remember, so theta was an unknown parameter. Okay? Theta in reality you might never know what is the true value of theta. You can actually guess. Okay, so you are basically measuring random variables that whose distribution depends on theta, and from the measurement of those random variables, uh, you want to estimate theta, let's say. Okay, and so that is the best you can do. You always do these things. You actually never measure, like most most in most cases you never measure the parameter directly. What you measure is are quantities that actually depends on that parameter, that I call theta, and looking at the pattern of those measure in the measurements, you try to guess the value of theta. Okay, for example, when again go back to the measurement of Young's modulus. Okay, so for a bar, you do not directly measure Young's modulus. Okay, so you know that Young's modulus influences that if you hang 1 kilogram of weight from that bar, how much will it depreciate. So those are the random variables, and those random variables, those depreciation values that you are measuring, those little things, little quantities that you are measuring, they are influenced by this Young's modulus. Okay, so from a measurement of those, you are trying to estimate the Young's modulus there. Okay, so far this should be clear. Okay, so what you are trying then, in a sense, is that given these values, okay, so this x1 x2 and xn, you say that your theta, the estimate of theta, that you usually denote by theta hat. Okay, and so theta hat can in general depend on these, because these are the actual numbers that you have measured. Okay, so theta hat would be a function of x1 x2 and blah 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 xn. Okay, and so you construct a function. How to construct this function that actually estimate theta, that is another problem. But so far it should be clear that since these are the only information available, then you have this theta, this estimate of theta, okay, here. Okay. Now, so remember, so what I told you is that this x thing has a distribution, right? Fx theta has a distribution. So here is x. Suppose this is my fx theta, and for a particular value of theta, so for a particular value of theta, you get such a distribution of f. Okay, and and remember, since you are measuring this only for a finite time, okay. Now, if you could measure this for infinite times, like if you had infinite entries in here, okay, in here, if you had infinite entries, then you could actually retrace this distribution with arbitrary low precision, okay, or arbitrary high precision, let's say. So you populate everywhere and you can actually reconstruct this continuous graph. Since this continuous graph actually uh, uh, is unique to this value of theta, then looking at that continuous graph, provided you had the luxury of this infinite sample size, by the way, this n will be called the sample size, okay, then you could actually uniquely pin down with arbitrary precision. You could uniquely pin down then sorry you could uniquely pin down the value of theta, okay. So so now the estimate of this theta, which I will call it by theta hat, it would be said to be consistent. So if the probability, so it is this is how it is expressed here. So in the limit n tends to infinity, the probability of observing this theta hat in the epsilon neighborhood of theta, if this epsilon is finite, is equals to 0. That means theta hat will, in the limit that your sample size is infinite, then this theta hat should reduce to theta. You should be able to uniquely say what value of theta gives me such a distribution, such a nice distribution, only if you had the luxury of infinite sample size. But in reality, you never have the sample size to be infinity. Okay, you have just n number of data. Okay, this n can be large, but it's still a finite. Now, this uh, uh, since this thing is finite, and the experiment basically measures this n independent value of this x. So this thing together would be will be defined as my experiment. So remember, so the experiment means measuring the values of x independently small n times. Okay, so these n values together consist uh, in an experiment. Okay, so that is uh, how I say this is my random experiment actually. So this is the definition of my experiment. Now here is the important thing. So from these values you have actually get an estimate of theta. In in theory, in terms of uh, theoretical understanding, what you do is that, so before you actually go into doing an experiment, by experiment I mean you go into measuring x this n times independently, you have a strategy how to extract this theta hat in here. So what you have here is basically a functional form in terms of x1, x2, and xn. So if I am talking about the functional form here, without ascribing any particular numerical values to x1, x2, and dot 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 up to xn, then that quantity will be called an estimator. Okay? So I want these two terms distinctly visible so that you do not confuse them. I will be using same symbols for estimator and estimate as usually done in the statistics literature. The only difference is by estimator I mean the functional form in terms of this x1, x2, xn without appealing to a particular value of this of these measurements of x1, x2, dot 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 up to xn. Uh, but when I put in particular values of x1, x2, when I actually plug in my actual measured values of these n quantities, then what I get is an estimate of theta. Okay. Now, so remember, if your actual value of theta, the true value of theta, this is denoted by just theta without any suffix or prefix, that is still unknown. But from this measurement, you hope that you can construct an estimator that will get you to sufficiently close range of this theta. How close, that is a discussion for another class. Okay, but you hope that you construct this x1, x2, xn in such a way, in terms of this, in such a way, so that this theta bar is can be taken as an estimate of this true value of theta. Now, why you say that this theta bar can uh, uh, never give, not never, can only be an approximation of the true value, but we will never know the true value, because this theta bar is a random variable itself, or this theta hat is a random variable itself. Okay, it's a random variable itself. Okay. So this is a statistic that you have constructed with this x1, x2, xn. It's a random variable itself, because if you want to repeat your experiment, okay, so basically under repeat under to repeat your experiment, then what do you mean by repeating your experiment? You are basically measuring this n number of x values many different times. So suppose in the first go you have measured x1, x2, and dot 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 xn. These are your values. Suppose these, and in the second try you get x1 prime, x2 prime, dot 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 up to xn prime. In the third measurement you got x1 double prime, x2 double prime, blah 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 up to xn double prime, and so on. So you understand this thing. So you are measuring the same set. So this is experiment 1. So this is my experiment 1. This is my experiment 2. This is my experiment 3. Okay, and so on. So you are repeating your experiment, and you are going to get different measured values. Now these are no, I mean, when I talk about a specific experiment, these are actually values. So this has a value of, let's say, 1.02. Okay, this has a value of, let's say, 1.95, whatever. So these are random values. Now when you repeat those experiments, you are doing the same experiment again. If you had gotten 1.02 here, you are no longer bound to get x1 prime equals exactly equals 1.02. Okay, so now you notice that if you make an estimate of theta bar here or theta hat here, that will be different from the estimate theta hat from here. Although you are plugging in the same functional form, since the argument of these functions are different under different experiments, if you repeat the experiment, then this estimates will also vary. Okay, so this estimates are subjected to fluctuation uh, on this under the repetition of the experiment. Okay, so given so if you have constructed a functional form of this theta hat involving this x1 x2 dot 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 xn, since these x values are already being sampled from this fx, which again implicitly depends on theta, that means this theta hat is a random variable which will get every time it will spill you different values. So if I actually do this experiment in my mind, repeat this experiment say infinite number of times. Remember, by experiment I only mean a fixed number of measurements, n number of measurements. It is not that in experiment 1 I do 10 measurements and in experiment 2 I do 20 measurements. No, the number of measurements are also the same. That is how I define my experiments to be. The point is, if I in my mind repeat these experiments, then for every experiment I will get different value of theta hat. Okay, so this theta hat will also be a random variable whose distribution will be given by another PDF, which I denote by G. So G, like, which gives you the distribution of theta hat, and this distribution quite presumably will also depend on theta, because the sample uh, x, so what values of x you are expected to get under repetition of experiment depends on theta. So this distribution of this theta hat, the distribution of the estimator, will also implicitly depend on theta. Okay, and this I will call as my sampling distribution. Okay, so this is my sampling distribution. So remember, given a choice of this estimator, so once you have decided on the functional form of an estimator, your uh, your sampling distribution has been determined. So given the functional form of the estimator, then so for a given uh, theta hat x, uh, g theta hat theta is determined. Okay, so now if you choose a different functional form of this estimator, then you will get a different distribution. Okay, so let me draw the sketch of those distribution in this way. So in this axis you have theta hat, and in the y-axis you have g theta hat given theta. And suppose this is so this I notice that this is my g1 theta hat theta. So g1 means for a particular choice of this theta hat I have this distribution. For another choice, if somebody chooses something else, then that person might have a distribution like this. Okay, so this is, let's say, g2 theta hat theta. So that is for the choice of a different um, mm, different estimator for theta. Okay, so you will get different sampling distribution depending on the functional form of this estimator. Okay, now first let me know you understand, all of you understand the concept of sampling distribution here, and if there are queries you ask me now before I proceed further. Okay, so all right, I guess there are no questions then, so I will proceed. So first thing you need to understand that there are a few things involving the sampling distribution. So first thing is the expectation value of this theta hat. Okay, so the expectation value of this theta hat will be this theta hat times the sampling distribution and then d theta hat. Okay, now this is the same if I use my old distribution. So the old distribution will be, so remember I am observing x1 x2 dot 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 up to xn, and I am measuring these things independently. So if I measure these things independently, then the combined probability distribution of this measurement is to observe x1 here and x2 in the next and so on will be just the product of the individual PDFs. Okay, so the probability distribution will just be f x1 given theta, then blah 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 up to f xn given theta. Okay, dx1 up to dxn, and then you multiply with this theta hat, which is a function of x, and you get this expectation value. Okay, now when you know this expectation value, then you can define something called a bias of an estimator. Okay, so the bias of an estimator is defined to be, so this is denoted by b, which of course can in general depend on theta, so I will call the b the function of theta, will be the expectation value of theta hat minus theta. That means if uh, the expectation value of theta hat coincides with the true value of theta, then the bias for that estimator will be 0. Okay. Now, for example, let's say the true value of theta is somewhere over here. Okay, and you see for the blue distribution, the expectation value will lie somewhere very close here. Okay. So this is also the expectation value of theta hat. Now this so just because this has nearly zero bias, okay, it doesn't mean that we should always choose this particular estimator corresponding to this blue curve. Okay, so the minimum bias is sometimes a good thing to have, but you do not usually discard an estimator just because it might have a finite bias. Okay, there are other things to consider. Remember, there is also the width of this distribution. So for the blue distribution, you see that the width is higher, and the for the uh, orange distribution, the width is lower. Okay, so in this case, that I so this is my expectation value of theta hat in here, and this is a lower width. Now, what does the width of the sampling distribution give you? Okay, so the width of the sampling distribution, that I will call the statistical uncertainty of the estimator. Okay. Okay. So this I will denote by sigma theta hat, these things. So this is the kind of the statistical uncertainty, or basically statistical deviation, or yeah, uncertainty of the estimator. So this actually tells you how reproducible are your experiments, like how reproducible your experiments are. Okay, so remember, if you take the blue curve, okay, if you take the blue curve, then if for one random experiment, for one experiment that so when I talk about experiment now, I mean in this sense, I am doing experiments. So if in one random experiment you get a value of theta hat here, and even in the second experiment you will get a value of theta hat somewhere over here, and in the third experiment you will get theta hat here and here. So the theta hat can be everywhere. If you repeat the experiment, then the and your theta hat obeys this blue sampling distribution, then that means that your experimental results, so you know that at the end you will be quoting a value, an estimate of theta, right? Now, as I told you, this estimate is going to fluctuate, right? And it is it is subjected to fluctuation when I repeat my experiment. So when you give an estimate for a parameter, you need to specify how confident a person will be in your estimate for that parameter. And that level of confidence, that how reproducible your estimate is, uh, when I take into account the repetition of my random experiment, will be given by the precisely the width of the sampling distribution, because the width of the sampling distribution is the thing that actually takes into account the statistical fluctuation in here. So although this theta hat, this particular definition of theta hat gives you zero bias, almost zero bias, then it does not necessarily mean that it will be a good estimator, because if you estimate the using this estimator, then you cannot be very confident in your estimate. Whereas if you take the orange thing, although you are away from this true value of theta, somehow, if I usually do not know the true value of theta, but actually for some cases, let us say that we know for some reason. Okay, we will see how that happens. Now, if we are here, although we are away from the true value of theta, but we can be very confident in my estimate of this orange estimator. Okay, because even if I repeat my experiment, my other values will lie very close uh, to this value, so it will not fluctuate this much in the previous, in the previous case. So although it has a finite bias, I might find this estimator to be better suited to get my parameter theta, uh, instead of the blue estimator, which might have a finite, which might have a zero bias. Okay, so in this case, since the average distance So this is kind of my B, right? So this is my bias B. So it has a finite bias. So if I know the bias from this estimate of theta hat, from this orange estimate of theta hat, I can get a value of theta just by subtracting the bias. So that's why this bias in many cases are said to contribute to the systematic uncertainty. This contributes towards the systematic uncertainty. All right. So this is a kind of a perfect example uh, of this uh, let's say theory of errors, where you have probably learned about statistical error and systematic errors. So remember, the statistical errors are mostly related to the statistical fluctuations of the estimator themselves, and that is dictated by the width of the sampling distribution. Whereas the systematic error, as the name suggests, is present in a systematic manner. Okay, so you are trying to get uh, a true value of theta. You are trying to get as close to the true value of theta, but you have constructed an estimator such that you always land on a finite distance from the true value, and you can, in some cases, you can guess that distance, which you will call the bias. But even if you land away from the true value of theta, you can estimate, your estimate for that estimator is statistically very robust. Okay, because of the sampling distribution is very narrow. Okay, so you might choose in that case, even if that is an estimator with a finite bias, you might prefer that estimator uh, instead of this. Okay, so uh, so there is always this compromise. So if you want to um, construct an estimator with a zero bias, you often end up with an estimator with large statistical uncertainty, large sigma theta hat. And if you want to construct an estimator with with a low statistical uncertainty, you actually end up invoking a finite amount of bias in your definition of the estimator. So for that case, when it comes to the compromise, so people usually define this quantity called the mean squared error. Okay, so the mean squared error, and it is sometimes called the MSE. Okay, and this dictates the quality of an estimator. Okay, and it is defined as, so this MSE is defined as the expectation value of theta hat minus theta whole square. So it kind of takes into account both these things. Okay, so it takes into account expectation value of theta square, which is connected to uh, the statistical uncertainty of the distribution, and the other thing as well. Okay, so now if you basically add and subtract expectation value of theta var, I ask you to actually prove this thing. So this is equivalent to, it is quite simple. Okay. So expectation value of say theta hat minus expectation value uh, of theta hat this whole square plus then expectation value of theta hat minus theta this whole square. Okay, so notice here that here the expectation value is in inside, and here the expectation value is, so you first you take the square and then you take the expectation value. So pay particular attention to the brackets, and you should check this actually. So now if you notice, so this thing, this theta hat minus expectation value theta hat whole square, this thing precisely is the statistical uncertainty of this thing. So this is variance of theta hat or sigma theta square. Okay, so this is basically variance of theta hat for that particular distribution, and then this is the bias square. Okay, so it doesn't matter whether you have a positive bias or a negative bias, since you are squaring, so any non-zero bias will reflect in here. And this v of theta hat is nothing but this sigma theta hat square. Okay, this is the statistical uncertainty of the estimator. Okay, so to make this compromise, if you construct an estimator to check the quality, how good is your estimator is, you try to minimize the mean squared error. Okay, and if you are happy with that estimator that has a low enough mean squared error, then you proceed with that estimator. Okay, so this is the these are the general properties of an estimator. Okay, now any questions up until here? Any questions? No. Okay, so let me proceed then. Okay. So let us say that the estimators for mean, variance and covariance. So I will do the covariance later. Just do that. So first, let us start with the most basic quantity that you might be interested in. Okay. So your x might be distributed according to a distribution fx. Uh, there might be parameters involved or might not be parameters involved, whatever that is. Okay. So suppose the distribution is fx, I am suppressing the parameters for now, but in general they might be there. Okay. And you do not know what these distribution are. Okay. What someone so someone actually comes and gives you, hey, I have made n independent measurements of this x, and I have gotten this value. So this x equals again x1, x2 up to xn. Okay, I have gotten these values, and he tells and he asks you that, can you tell me what can be the mean value of this distribution from these values? What is the mean? Okay, what can you say about the mean? Okay, so what can be an estimate or estimate or estimator in the same sense for the mean? Okay. Now you are puzzled because you are sure that this the mean will depend on this fx, right? So the mean, if you do not specify the distribution, then then how can I say anything, right? But you know something, that these values that the second person has obtained are actually inherently dependent on this fx. Okay. Uh, now, so these values are sampled from this fx. Okay, so this fx was different, then these sample values you expect ideally will be different for a sufficiently large number of sample values. Ideally, it would be different. So you can try to construct a quantity that you will call the estimator for the mean, and that you hope will capture the properties of this fx, so that if you change this fx, that estimator will change in such a way so that it always captures the effect of mean. Okay, so if you change this fx, then inherently this will be reshuffled, and these will take another values. So what can be the estimate for this mean? Okay. So as it happens, the arithmetic mean. So remember, you do not know the fx as it is. Okay, so that person doesn't tell you. I do not know what distribution it follows, but I got these values. So what can I say about this mean? Okay. So then you say, okay, I think the estimator for this mean, okay, that you call as mu hat, is 1 over n summation over I equals 1 to n xi. Okay, that's the arithmetic mean, just the arithmetic mean. The uh, arithmetic mean. Okay, now let us check whether uh, it is consistent or not. So remember, if I take the expectation value of mu, then this is 1 by n summation over I equals n. Then this is expectation value of xi, right? So I can try to break it down for your visual convenience. So this is expectation value of x1 plus expectation value of x2 plus dot 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 plus expectation value of xn. All right. Now, what are these expectation values? These are again subjected to the repetition of this experiment, what you would expect as the expectation value of x1. So suppose you make many such measurements, then here as you get x1, and then here you get x1 prime, then the third experiment you get x1 double prime, and so on. So what are the averages of these x1's entries? Since these are sampled according to fx, so these averages will be the average of this fx, and if that is mu, if that mean is mu without the hat, by the way, then this is mu. Since x2 is also sampled from the same fx, then this is also mu, and so on. So this is just 1 by n times mu, and this cancels out, and this is equals to mu, and this is the true mean. So this mu is nothing but the true mean, although you do not know the true mean. So true mean of fx. Okay, although you do not know, but you know that if you construct an estimator in this way, then the expectation value of this estimator is precisely equal to the true value of that parameter. So that means such an estimator has zero bias. Okay. So this estimator for the mean has absolutely zero bias. Okay. So this is the now again, if you construct now again this person comes to you with these values, and then the person asks, okay, what can be an estimate for the variance of the distribution? So this fx will have a variance from these values, from this one measurement. What can I say about the variance of this distribution fx? Now, as it happens, you can also construct it pretty easily. Okay, so that construction, so this is sigma square. This is sometimes called the sample variance. Okay, so that you estimate as 1 minus 1 by n minus 1, I equals 1 to n, and then xi minus the estimator of mean whole square. Okay, so this mu is given by this again. So the true value is not known, right? This true value mu is not known because the distribution itself is not known. I have made undetermined things. So remember, when you construct an estimator, on the right hand side you can only have the known quantities. The known quantities are those values of x's. Okay, so this x1, x2, x3, and that you have measured. Okay, and so that is how you constructed a variance that you call a sample variance. And if you actually simplify this, so basically you simplify this with this substitution and you put it back here, then you actually have n over n minus 1, then we have 1 by n summation over I equals 1 to n xi square minus mu hat square. Okay, so there are two terms. So remember, do this carefully. Okay, so this, from this you will get this. Now this quantity, I will call it the average of x square. So I will denote it by x square bar, kind of a mean square velocity for people with physics and chemistry. And this is minus mu square. Okay, so this is kind of the average of xi square. Okay. Now notice that the factor is 1 over n minus 1. You might be tempted to think, why do I not write 1 over n? If you write 1 over n here, that would be another estimator for variance or for something else. Okay, if you are comparing it with variance. So if you put 1 over n here instead of n minus 1, then it would be another estimator for that variance. Okay, nobody forced you to do. You could have put 1 by n minus 2. Nobody had forced you this way. But I have put here 1 by n minus 1 so that this estimator for the variance has a zero bias. So this n minus n 1 factor will ensure that sigma hat square has zero bias. Okay. How do you check that? Okay. Then you have to calculate the expectation value of sigma square. So to check it, to check this explicitly, we need to calculate the expectation value of sigma square, sigma hat square here. Now, in the language of this, we need to calculate two things: the expectation value of this guy and the expectation value of this guy. Okay. These two things I need to need to compute. So first of all, I notice that let us try to see what this mu square is. So this mu square is mu times mu, right? Okay, mu hat times mu hat square. This is the estimator. And the first mu hat I may write summation over I xi. Then I can no longer use I because it's a dummy index which I have exhausted. So I write j xj. So this is my mu times mu. Okay. So now if I am considering expectation value of mu hat square, then that gives me this is 1 over n square times expectation value of summation over I xi summation over j xj from this here. So I take the summation over I and j outside is 1 over n square. Summation over I and j goes outside, and this is just expectation value of xi xj. Now notice that there are two types of terms. Okay, so it tells you that if the terms are diagonal, so this is there are two indices I and j. So there are terms for I equals j, and how many terms are there? There are n terms, so there are n such terms. Okay, and then there is I not equals j. So these are off diagonal terms. So how many terms are there? The total number of terms are n square because n I runs from 1 to n and j runs from 1 to n, and n diagonal terms, so you have n square minus n terms. Okay, so you compute those two things separately. So for diagonal terms, so for I equals j, so this expectation value of xi xj, this thing reduces to expectation value of xi square. Now again, these individual x's, this x1 or x2 or x3, they are sampled according to fx. Okay, so then what is this xi square? If I remember that my for any xi, my definition of sigma square is that this is expectation value of x square minus mu square, right? This mu is the true mean and this is the true sigma. So this is the true variance and this is the true mean, because this is coming from fx. So this relation is coming from fx itself. And since these xi's are sampled from this fx, okay, so that means this expectation value of x square is a sigma square plus mu square. Okay. Now for I not equals z, then expectation value of xi times xj is just, since this xi and xj are independent measurements, there are no correlation between them. So this is expectation value of xi times expectation value of xj. Okay, and that, so this is mu and this is mu again, so this together is mu square. So if I plug this in here, so this expectation value of this mu square, this becomes 1 by n square. Then in the thing I have n diagonal terms, so n times sigma square plus mu square, right? So this is my n times sigma square plus mu square plus n square minus n of diagonal term, that is just mu square. All right. So now if you simplify this thing, then you will simply get sigma square over n plus mu square. Remember, this sigma and mu on the right hand side at the true values of sigma and mu respectively. Okay. Now in the same way, what I get, so this is my expectation value of mu hat square. Now what is the expectation value of x bars, or x square bar rather? So expectation value of x square bar is 1 over n summation over I expectation value of xi square, right? So because that is the definition of x square bar. So x square bar is this. So if you take the expectation value of this thing, then that gives you 1 over n times expectation value of xy square. Okay, cool. So now this thing is the same for everyone, and this is just, we saw that this is a sigma square plus mu square. All right. Now again, for every I it is sigma square plus mu square. Now you are summing from I equals 1 to n. This is n times sigma square plus mu square. So this is 1 over n times sigma square plus mu square. This n cancel. This is a sigma square plus mu square. Now let us go back. So now I can try to calculate the expectation value of sigma square hat. So that was n over n minus 1 according to my thing. So the expectation value of x square bar minus expectation value of mu hat square. All right. So you check this in here, this n by n minus 1 total global factor that comes out. The expectation value of this minus expectation value of this. All right. Now if you actually substitute these values, so this is sigma square plus mu square, and this is minus sigma square by n minus mu square. Okay, so if you plug this, so that means this mu square cancels out. So this leaves you with n over n minus 1 times sigma square times 1 minus 1 over n, which is exactly the opposite of this thing. Okay, so this will cancel with this, and you will be left with only sigma square. So you see that if you define sigma hat square in the way I did with a denominator 1 by n minus 1, then this becomes an unbiased estimator for sigma square. So this, you can say that sigma hat square is an unbiased estimator for sigma square. Okay, so that is something good to have. So in the same way, you could see that if you instead had 1 over n instead of 1 over n square, then this would not be sigma square. So suppose you actually have some, let me call it sigma prime hat square. So that was like 1 over n times summation over I, then xi minus mu hat whole square. So this is the definition you might be used to with, right? You would be tempted to define. So this is n minus 1 over n times sigma hat square. Okay. So if you actually try to calculate the expectation value of sigma hat square, so now you can see from this knowledge that n minus 1 over n times expectation value of sigma hat square, and since this expectation value of sigma hat square is sigma square as I shown you, so this n minus 1 by n times sigma square. So this is not exactly equal to the this is not exactly equal to the sigma square, but it becomes equal to sigma square if your n is large. So in the limit n is much greater than 1, it doesn't matter whether you are using sigma prime or you are using sigma hat square. They are both almost unbiased, and you can take one for the other. Okay. There is another interesting thing that I will mention before I close today's discussion. So remember, so all these things are basically estimates, right? So you are starting with the functional form. I did not tell you how this functional form come from. That would be the content of the next discussion. For now, we are getting these estimators just by plain guessing. So who told me that the functional form of this estimator for mu will be just the arithmetic sum of this exercise? Nobody told me. I just guessed from the way I construct mean and variance and so on and so forth. I just guessed it. Okay. Now, now comes the important bit. Okay. So remember, my original problem was that one person comes with these measurements, this x1, x2, and blah 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 up to xn, and that person asks you, "Hey, give me a guess for the mean. Give me an estimate for the mean." And what you did is that you just summed these entries, this whatever this guy gave you, you just summed these entries, this x1 plus x2 plus dot 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 up to xn. You divided by n, and you say, okay, you have it. This is the best guess for your mean. Now this guy asks you a more interesting question: how strongly do I trust this guess? Okay. Like, how confident you are with this guess? See, this question is tricky. That means if another guy comes with a similar set of measurement and you again calculate the mean, that will never be exactly equal to the first mean. So it will deviate from this thing. So if you collect all such measurements, if you not measurements, if you collect all such experiments, suppose 100 people comes, say they do the same experiment. That means 100 people are doing this same experiment, and 100 people are coming to you and asking you to calculate mean every time. So if you actually plot this mu hat, and you will get different values different times you will get different values. Okay. And the frequency of getting this will be different. That's the sampling distribution. So now this person is asking, how narrow is the sampling distribution, or uh, how can I get the error in this? So this will spill a number. Suppose this is 2.03. Okay, so suppose you get after mu hat, it is 2.03. So from one measurement, you get 2.03. Now you know that when you quote these values, when you quote these experiments, experimental values, so this is, you have to say 2.03 plus minus something. Okay, because if another person comes, you will not get exactly 2.03. So what is the leeway? What is the tolerance level of this number? You put something here. Okay. What do you put? You precisely put the statistical error in this mu here. Okay. So the statistical error in this mu that I call as sigma mu. So sigma hat mu hat actually I would say. So now that is given by the variance of the sampling distribution. So the variance of the sampling distribution of this mu will be the expectation value of mu square minus expectation value of mu this whole square. So that is the statistical uncertainty in the sampling distribution itself. Okay, everybody understands that. And a few moments ago, we calculated both of these. So this expectation value of mu square was my sigma square over n plus mu square. And since this is a zero bias estimator, expectation value of mu hat is just mu. So this is minus mu square. Mu square cancels out. And this is sigma square over n. Now remember, so your objective when you estimate your parameter, your objective is to reduce the error. You want to be as confident as can be in your estimation of your parameters. That means you need to reduce this, which implies you need to reduce this. How can you reduce this? There are two ways. One way you cannot control, and another way you can control. One way to reduce this would be reduce sigma square itself, the sigma upstairs itself, if you reduce that. So, but this sigma is the property of the parent distribution, this fx, which you have no idea about. So this you cannot control. Okay. So of course, the a statistical error in my estimate will reduce if I reduce the error in my mother distribution, this fx. If this fx is very narrow, then of course the x's you sample from this fx will be very close to this thing, this average, because every time you pick one x in random, you will be very close to this. So inherently your sigma square will be very small. Okay, that's fine. But you do not have the control over this. You do not know what sampling distribution is comes from. Then what is the other thing you can do? You can increase n. So that is, if you increase your sample size, if you do many measurements on this axis, the larger is the sample. So the same thing you are measuring, but measuring time and again, the larger is the sample, the lower is the variance of the sampling distribution. Okay, and this is the kind of the holy grail of statistics. This is what I mean. This is what we mean when we say that we do not have enough data. We do not have enough data to uh, be confident about our measurements. Okay, so as you accumulate more data, okay, as you accumulate more data, you become more confident in your estimates of your parameter. Okay, so the more data you accumulate, your estimates becomes more precise, because the statistical uncertainty, okay, the uncertainty due to statistics becomes reduced as you accumulate more data. So you become more precise in your statements about the estimates of your parameters. Okay, so I will close today's discussion here, and now let me know if there are questions. Otherwise, we will meet again someday this week before the mid-semester exam.
Sir, kindly tell about midsem means what should we prepare like from these lectures and the pattern of exam, something.
Um, I mean, you should not worry about the exams as long as you follow these lectures. Maybe I will give some simple problems or some simple calculations to do, and that can be done within 2 hours time. Maybe you will see a graph and you have to do something with the graph. So be ready with your computers at least. That is something you should do. You should keep
Uh,
your computer available with you.
okay, sir. And sir, please share previous lectures also.
Okay, did I not share? Okay, if I did not, then I will share those.
Yeah, okay, sir. Thank you.
Yeah. Anything else?